too small. Okay. Okay, I think it's time to start. So, any question from this time? This time we introduce this idea of density operators. This is how we want to describe. So the motivation is we want to describe a classical probability mixture of quantum states. Okay, and here important concept you should have is that classical probability and quantum superposition are different. Okay. But anyway, so now we have a classical probability mixture of quantum states. So suppose we are having quantum states, a lot of different quantum states with different probability pi, and we want to see how the system described by this probability mixture works, and you can just calculate this quantity called density matrix. Okay, so this is a matrix draw that is just equal to average over those projector onto the states. So it's summing over IPI, so the probability of each vector, and then the column vector times the row vector. So this is a matrix. This is a projection matrix onto the pure state. Okay. So and we say this quantity called the density operator will totally describe your quantum system in this classical probability mixture. And we give a rough example. We see that we can have two different probability mixtures that give you the same quantum state. So probability mixture of one half probability being a 0 state, one half probability being a 1 state. And you see that the calculated density matrix is this 1 over 2 times the identity matrix. And similarly, 1 over 2 probability being the plus state and the 1 over 2 probability being the minus state also give you the density matrix that's 1 over 2 times the identity matrix. And we are saying they have the same density matrix, so even though those two ensembles look very different, they are actually the same and you cannot distinguish between them, which we will see today. Okay, any questions so far? Yeah. And if not, then let's see how we describe the evolution of ensembles through density operators or density matrices. Okay, so we assume we are in some ensemble of pi and psi, and then we think about how the states in the system will evolve when you apply some operator. So we say, well, the evolution of a quantum system is described by some unitary. So we think some unitary, so we think the system is getting applied by some unitary u. Then each state is going to become u psi. That's how pure state evolves through our quantum postulate. Okay, so each state psi will become ui, and this evolution should not change the probability distribution. So each one still have the probability pi. Okay, so you start with an ensemble of pi and psi. Then after the evolution, you should have an ensemble of pi and u psi. Okay? And let's see how the density operator evolved. Okay, so there's before the evolution, we can write down just by definition of the density operator of density matrix it is summation I pi, then there's a psi I psi, and then after evolution, we can write this also by definition. So it's the pi and the projector onto u psi. So u psi and the psi u dagger. Okay. So after evolution is this thing, and now we use linearity. We see that this matrix multiplication is linear. So you can put a pi inside and also summation I inside, and you see it's U and U dagger sandwiching this summation I pi psi psi, and this is just rho. And so you see that after evolution, the density matrix between U rho U dagger. And what's good about this formula is that this formula you can describe it just by rho. You don't need to. Is U rho U dagger? You can just written it down with rho. You don't need to know the details about pi and psi. You just know this is something that depends on U only. Sorry, something depends on rho, U and rho only. So yeah, so before evolution, your density matrix is rho. Then after evolution, your density matrix is U rho U dagger. Okay, so we can describe the density matrix after evolution. Okay, and there's evolution, and the next thing we want to show is measurement. And so here is how you get the classical information out of the quantum system. And we want to show that whatever classical information you can get out of the quantum system is described by your density matrix, and also the post-measurement state is described by your density matrix. Okay, and yeah, so let's start with our derivation. So let's start with setting up our system. So once again, we have example of pure states. We have those example of pure states, so probability pi and whole bunch of probability pi and a whole bunch of states I. And then we are also going to do a measurement. So suppose we have the generalized measurement described by those measurement operator m, big M, some small m. Yeah. And then yeah, so let's do the derivation slowly. So let's see what each individual state will become after the measurement. Okay. So if your initial state was some psi, and by the measurement rule we talked before, the probability of getting outcome m. Okay. So we want to see what's the outcome probability of the probability of each outcome small m. Okay. So probability of outcome m, given the state is I, so we have this conditional probability here. So it's the probability of outcome being m, given that the input state is I. This is just the formula we had before. So it's m sub big small n times psi is non square, and so that's this thing inner product with itself. So it's a psi and m dagger m psi, and then once again we can use the trace trick we have. So this is just a number, so it's a trace itself, and then we use the cyclic property of trace, and so we use the cyclic property of trace, and we move this psi to the end. Okay, so we move this psi brought to the end, and we see that this thing is trace m dagger m m dagger m times psi. Okay, and so that's the probability of your getting outcome n when the input is I. And now we want to know the total probability of getting outcome n when you are given this example of pure state. Okay, so this is basically why we need to use base rule. Okay, so the chain rule of probability. So the total outcome probability is the conditional probability times the probability that you have the pi start with. So so summation I, you start with state psi times if you have state I and you get outcome n. Okay, so this is the total probability of getting outcome n. Then this thing, and we plug in formula. So it is summation pi just from this pi, and the probability p condition on m we have it here. So it is trace m dagger and psi psi. Okay, and here once again we use trace is linear, and matrix multiplication is linear. So we put this pi here and the summation I here, and we see that summation I pi psi psi once again is our density matrix. So this is just the trace m dagger m and rho. Okay, so we see that once again the outcome probability of a particular outcome m doesn't directly depend on your pi and psi. You can just return it as a function of your rho. Okay, so it's a trace m dagger m rho. Yeah, so this means that even if you might have different pi and psi, as long as your examples have the same rho, you will have the same outcome probability. Okay. and so the outcome probability is the same, and we want to see the post-measurement states are also the same. Okay. And when we say post-measurement state, we actually means the post-measurement density matrix. Okay, so initial state, and but anyway, let's see the post-measurement state. Okay, so once again, let's do the each initial state first. So if you have an initial state being psi, and you have outcome m, so here we should say the post-measurement state with outcome m. With outcome m. Okay, so if your initial state is psi, then the post-measurement state with outcome m is nm psi normalized. Okay, and yeah, and then we need to. So this is if the initial state is this thing, and now we need to do a kind of a hard calculation. We want to say now we have a lot of different states. Okay. Alright, so now we have the input state being different size with different probability. Then we want to see what's the outcome density matrix. Okay, so so yeah, so we will have a different post outcome state with different probability. Okay, and yeah, so now we want to see the density matrix after the measurement outcome. Okay, the post measurement density operator. And when you have outcome m. And now this is a little tricky because unlike here, so here the probability you can just sum them together, but but here is the calculation is a bit tricky because different input state has different probability of getting outcome m. So after you do the measurement, the probability of those ensemble probability is going to be different because you are selecting on you getting outcome m. So the weight between between those psi m is going to be not just pi, it's going to be pi condition you have outcome m. Okay? So our post-measurement density matrix should be the summation I probability of I given that your input state is m. This pim is not the same as pi because pni is different for API. Okay, so you have probability of input being I, condition on outcome is m, and then okay. So here we have we are also writing this as just as a definition. So summation the probability of post-measurement outcome being I, and then projector onto the post-measurement state psi mi. Okay, and now we just write down the formula summation p I condition on m. And then this thing projector on this thing, so that's n psi and mm dagger, and then this thing square is just psi n dagger n psi. Okay, and okay, so now the hard part is p of I condition on m, and to know what's the p of I condition on m, we use the probability theory. Okay, and probability theory says that basically, there is a base rule says probability of A condition on B equal to probability A times probability B condition on A divided by probability B. And the derivation of this thing is because, let's see. Okay, that's because if you multiply probability B to the other side, okay, so let's do a quick derivation of the base rule. That's because the probability A condition on B times probability B equal to probability both A, B happen. Okay, so this is probability A and B both happen, and that's also equal to probability P condition on A times probability A. Okay, but anyway, this is probability theory. And so now we want to see probability P I condition on M, and we actually know all three other things. Okay, and so the probability P of I condition on M is probability I divided by probability M times probability N condition on I. Okay, and so we have all those things here. So probability I is probability is just a given thing. It's input probability of each state I, And the probability n condition on I, we calculated 2 slides before. Is when input state is I, outcome is m. Okay? And it's just this inner product. And the probability m is, we also calculated 2 slides before, is trace m dagger and m row. Okay, so we just plug in everything here, and and we see that, so we skip ahead a little bit, and we see that this inner product here is actually same as probability Pn condition Pn condition I. So this is also equal to Pn condition I. And so what happened here is these two numbers cancel out. So the most ugly term cancel out. This conditional probability cancel out. And then we have probability I, and here we still have this m psi and dagger. And then we have Pn equal to trace m dagger and m row. Okay. And then finally we see that anything or the thing condition, or the thing that depend on I can be grouped together to some I, Pi, and this psi, and we know that's the density matrix row. So we put this summation Pi inside together with this psi, and once again that become row, and we see that the post-measurement density matrix is also something that only depends on the input density matrix. It is m row and dagger, and divided by trace and dagger and row. And I think an easy way to memorize this is you can just think the post-measurement state, kind of like when we have a pure state, we say the post-measurement state is m psi, right? And we need to normalize it. And here you can just think it's about the post. Okay, here the okay, and so here the quick way to memorize this is memorizing that you're just having this. Your post-measurement state is just you sandwiching your state with the measurement operator. So you have m row and dagger. And then you should normalize by dividing in trace, because later we'll show that all density operator has trace 1. So you divide by its trace, then you become trace 1. Okay, and you see that this has a similar form to the unitary evolution. So so unitary evolution, you sandwich your row with u and u dagger, and when you do measurement, you sandwich your state row with m and m dagger. Okay. Any question with this derivation? This is a bit more complicated. If not, So and then we complete what we can. So we see that the evolution and measurement of a density operator can all be described by the evolution and measurement outcome and the post-measurement state of example of quantum state can all be described by its density operator. So the density operator actually has the full information that you can get from the example of state. So you can just write down the density operator to represent an example of pure states. Okay. And now we have a little bit of definition and names here. So here we introduce two names: pure states and the mixed states. Okay, so we'll already be talking about pure states, and we haven't said what it means. It actually only have meaning when you also introduce mixed state. Okay. And so pure state is basically the quantum state we'll be talking about in previous chapters. Okay, so if your state can be written as a single, your quantum system can be written as a single complex vector in your Hilbert space, then it's a pure state. Okay, and then we know the density operator of a pure state, so it's just this state being 100%. So density operator is just the projector onto this state. So it is cyclic bra. Okay, and then compared to pure state, so pure state means it's very pure. It's 100% of just one component. Okay, so instead of pure state, we also have mixed state. Means that we have different state mixed together. And yeah, so it will be a mixture of different pure state. So it's a probability mixture of different state. Pure state is in some example row. Okay, and yeah, so pure state means that your density operator. Okay, so people actually. So here, the name of pure state is actually a bit ambiguous. Okay, so pure state. People will so you see that here we have a column vector and here we have this being a matrix, and the name pure state is actually quite ambiguously used. So you will either mean a density operator that can be written as this projector onto a single state, or it can just mean a single vector here. Okay, so either this vector or this density matrix that can be written as a projector out of a vector, people will both call them both as a pure state. Okay, so pure state is a bit of it has a bit of ambiguity because sometimes people means your vector is obviously a pure state, or they mean the density matrix is a pure state. Okay, but for mixed state, obviously it must be a density matrix. Okay, because by definition, a mixed state is something that cannot be described by just one vector. Okay, so there's a pure state and a mixed state, and we have a small theorem here that you can prove in your homework. And it says that so if you are just given a density matrix, how do you see quickly that whether it's pure state or mixed state? Is you can calculate its square and the trace of the density matrix squared. Okay, so if you square your state and take a trace, then and equal to 1, then means that your state is a pure state. Is if only if, and otherwise, if this thing is less than 1, and then you are in mixed state. Okay. Okay. And then let's talk about something interesting. Is that we have been describing example of pure state, right? Before we, as I say, in our example are composed of some probability mixture P of some states I. And you might think, okay, so we have said the probability mixture of pure states can be described by density matrices. But what if you stake this one level higher, and now we have probability mixture of mixed states? Okay, and it turns out that if you put even more probability inside, then you can still be described by mixed states. Okay, so whatever classical probability you put in your quantum system, they can all describe by mixed state. Okay, and yeah, so here we have a very short derivation, and we say that we have a probability mixture. Yeah, so it's written a little weird here. Okay, so here we are given a probability mixture Pi of density matrices rho I with probability Pi, and its density matrix also correspond to some example Pij and Psi ij. Okay, so it's a mix with respect to this. So each rho I is mixed with respect to this index j. Okay, so we have this two level of mixture. So with with Pij, then mix those Psi ij together to rho I. Then we have those rho I mixed together with probability Pi. And then we want to see what's the density matrix of this final mixture, and we see that is now once again we use this chain rule probability. So probability of you actually getting state Psi ij is going to be Pi times Pij. Okay, so it's going to be sum over ij and those Psi ij and with probability Pi times Pij. Okay. And here there is once again you simple linearity. Then you see that if you do deal with summation j together first, so if we resolve the summation of j first, so So J, so those J, and the J dependent terms are those Pij, Sij, Sij, and the summation J. And you see that when you do the summation on J first, then it's just rho I. That's the definition of rho I because because it is indexed by J here. Okay, so this thing just summation I, and so we'll leave it with the I term summation I Pi rho I. So here this very short derivation just says that if you have a probability mixture of density matrices, and then it actually has a very small formula to calculate. It's actually still a density matrix, and with a very simple formula to calculate it. It's just this averaging of your rho I. It's summation Pi rho I. Okay. So yeah, so you have a probability mixture of density matrices. It's very easy to calculate the resulting density matrix. Just summation Pi rho I. Okay. This thing here. And and here we can also define a density matrix that's kind of funny. That's related to measurement. Okay. So suppose you do there's some weird thing you can do to a quantum system that is that is you do you do a measurement on it, but you don't know the outcome value. Okay, and yeah, so this is okay. So let's go back to the quantum measurement first. So remember when we do quantum measurement, we will get the post-measurement state rho n, and each one has associated outcome probability. Okay, so we do measurement, and we will know as our postulate. We say we do measurement, then we will know we get some outcome m, and this thing happen with probability pa, and you have some post-measurement state. But sometimes you don't know the actual value of m. Okay. And this sounds a little dumb. It's like you throw it away, but actually we already seen this happening. That is, remember when we have teleportation, right? When we have teleportation, we say that Alice and Bob, can have some entangled state. So actually 2 qubit here, 1 qubit here, okay? And we say Alice and Bob have an entangled state. And Alice will do some measurement here, okay? And this measurement will change the total state, but Bob doesn't know the measurement outcome. Okay, so this measurement already changed the state. It changed the state to some probability mixture. Yeah, so Bob knows that Alice do some measurement, but so this measurement will change the total state, but on Bob's side he doesn't know the measurement outcome because Alice haven't tell him. Then Bob can describe this system as a probability mixture of post-measurement states. Okay, and then we actually have a very simple formula for describing the post-measurement state. Okay, so that's sum over all the measurement outcome, then the measurement outcome probability. Okay, this is the measurement outcome probability because we haven't learned m, and then the post-measurement state. Okay. And we already calculated both quantity before, and let's just plug in a formula. So the measurement probability is the trace of this n rho n dagger, and the post-measurement state is this n rho n dagger, then actually divided by this measurement probability to normalize it. Okay, so you see those two terms cancel out. And this thing has a simple formula of just summing over all the possible outcomes, and m rho and dagger. Yeah. Okay, so this is the example of post-measurement state. If you do the measurement but doesn't know the outcomes. Okay, and I guess this is important quantum effect to learn. To know is that this state is actually going to this state is very likely to be different from the input state. Okay. Here I should not say rho. Okay. So this is like a row prime. So the output state, the output state is this thing, and because the row is the input state. Okay, and yeah, so this output state, post measurement state, even though you didn't know the probability, is very likely to be not equal to row. Okay, not necessarily equal to row. Yeah. So let's see an example here. Okay, and yeah. So the example is we have a quantum state plus state. So this is the eigenstate of x, and we measure it in computational basis 0 and 1. Okay, and so the original density matrix of rho is this projector onto plus plus, and as we calculated before, this is 1/2 and 1 1 1 1. Okay, and then after measurement, the state is, so we plug in the formula, rho prime equal to, so here we use rho prime, so I guess here we also use rho prime. Okay, so here I should say rho prime, the post measurement state rho prime here. Okay, okay. And the post measurement state rho prime is the summation of measurement operator rho times the measurement operator square, dagger, excuse me. And so the measurement operator for the computational basis is 0 and 1 is projected onto 0 and projected onto 1. Okay. So 0, 0, 0, and then density matrix is plus plus and 0, 0, and 1, 1 plus plus 1, 1. And here we have simple calculation. So the calculation we do here is the middle part is number. So this broad times k is number, broad times k is number. And those number is overlap between 0 and plus is 1 over square root 2, and overlap between 1 and plus is also 1 over square root 2. So we just say 1 over 2. So so this part become 1 over 2. Excuse me. So this part become 1 over 2 is just a number. This part become 1 over 2 is just a number. So both of them 1 over 2. Then we left with projected onto 0 and projected onto 1 again. Okay. And yeah, and this is 1 over 2, this is 1 and 1. Once again, this is the identity matrix. And this also match with our expectation that we do a calculation before, saying that if you have 1 over 2 with 0 state and 1 over 2 excuse me, 1 over 2 probability with the 1 state, then the post measurement state is 1 over 2 times the identity matrix. Okay, and this thing is a very special mixed state. It's called totally mixed state or maximally mixed state. Basically means that it's 1 over the dimension times the identity matrix, because well, identity matrix is kind of special. It has equal probability on all the dimension here. Okay, and yeah. And I guess one more thing to see that this density matrix is actually different from this density matrix is we can check their measurement statistic. I guess it's easier to do. Let's see if you measure x operator on that. Okay, if you measure x operator on it. Okay, on that. If we measure x, then remember that measure x, and let's make it easy, and then we just want to see what's the expectation value of x on it. Okay, if your input state is plus plus, then expectation of x is equal to trace of plus plus on x, and this is equal to 1, because x on plus still equal to plus, and then that's the trace of plus plus, that's just equal to 1. Okay, and if you have the totally mixed state, 1 over 2 times the identity, and then then the expectation of x equal to trace of 1/2 times identity. Let's not write a parentheses. Okay. If your input state is 1/2 times identity, then the expectation value of x is 1/2 times identity times x. Then is a trace of 1/2 times identity. 1/2 times x. And because identity times x equal to x, and this is just equal to 0, because we know that trace of the x operator equal to 0. Okay. And yeah, so you see the expectation of x is different, and also this calculation here should check out, because if you measure x on plus state, then you just have probability 100%, you get a plus state out, which is +1 get state of x. And then if you measure x on this identity, you will see that you will get 1/2 probability getting plus, 1/2 probability of getting minus, which means that the expectation value is 1/2 of 1 plus 1/2 of -1 equal to 0. Okay. Any question on the post-measurement state as a mixed state? Yeah, and here I guess we can have another homework is then you can think about what's the post-measurement state when you do when we do the teleportation protocol. Yeah. Okay. And yeah, and we have 4 minutes. Okay, I think 4 minutes we don't have enough time to complete the proof of the next thing we want to say, but let's stay the theorem. Okay. And so we said a lot about density operator. We say they can characterize, totally characterize our ensemble, and we should just describe those ensembles by density operator because they have full information. And here we give even more strengthening of this result, and saying that you have an operator, we don't need to check whether it comes from some ensemble, because we can, an operator can come from some ensemble if you just check 2 simple property. Okay, so we say we can check whether a density operator, so this matrix is a valid density matrix if and only if it satisfies these 2 constraints. Okay. And the first one says that is trace equal to 1, that we kind of hinted, we have a spoiler before, and also that the rho is a PSD matrix. Okay, so it means that all the eigenvalue of rho are between 0 and 1. Yeah, also so this means that all the eigenvalues of rho are positive and real. Semi-positive and real, and this means that all the eigenvalues sum together to 1. Okay, so let's write down what this means in terms of eigenvalue. So rho is PSD, means rho can be written as summation I lambda I psi I, and so PSD means that all the psi i's are positive real, positive semi-definite, and trace trace rho equal to 1 means summation I psi I lambda I equal to 1. Okay, and yeah, this is actually part of proof, but we only have 2 minutes, so let's stop. Sorry, we actually have 10 more minutes, sorry. We are going to 4:20, right? Okay, so yeah, so let's see the proof of this theorem. Okay, and yeah, so there are 2 directions, and and we kind of already do the first step of the yeah, and yeah, so there are 2 directions. So we say this statement is true, is if only if. Okay, so we say rho is a density operator to some ensemble of density ensemble of pure states if only if it's both of those conditions are true. Okay, so the only if direction says that if rho comes out from some ensemble, then you have trace rho equal to 1 and rho is a PSD. Okay, and this is just a calculation. So we know rho is this summation I, pi, and psi I, psi. So trace I is a summation is a trace of this thing, and we know trace is linear. So it's a summation I, pi, trace psi, psi. And then we use the cyclic property of trace, then it's a psi inner product itself, and we know this is 1. So it's just summation I, pi, and but pi's are probabilities, and so they should sum to 1. Okay. And so you see that this trace rho equal to 1 just means the probability of this density matrix go to 1. So this is like a normalization. This is like a normalization of the density matrix. It is similar to saying that the length of your quantum state should equal to 1. Okay, and and then the second thing says that rho is a positive semi-definite operator. That means if you sandwich rho with any vector psi, it should be greater or equal to 0. And once again, we just plug in this brute force. So rho is this summation pi psi psi, and you sandwich with psi. But the summation and the pi are linear, so you can just put this psi inside to the actual matrix part. So you have the inner product between psi and psi, and psi between psi. And but those two things are complex conjugates to each other. So that's just psi inner product with psi inner product with psi and absolute value squared. Okay. And we still have summation I, pi. And so this thing is greater or equal to 0 because, well, it's absolute value squared, and pi is also greater or equal to 0. Then you sum over a whole bunch of greater or equal to 0 terms, is still greater or equal to 0. Okay, so this is a pretty direct calculation. And then the next one we kind of have the derivation already here. So the most important step is here. And it says that the rho is PSD, then it has a spatial decomposition rho equal to summation I, lambda I, here we use J, okay? Rho equal to summation J, lambda J, and Jj. So J is the eigenvector corresponding to eigenvalue lambda J. Okay? And yeah, and here we use the result that we stated in chapter 1. Okay. So our first week. So first week we say that I think we say this, but any SDP matrix can be unitary diagonalizable. Okay. So it can be written in this form: summation J, lambda J, J, J. Okay. And we have a short sketch of this claim. And it says that because your rho is semi-definite, and you can show that it's also Hermitian. And we have said that Hermitian matrices are unitary diagonalizable because it's normal. Okay, but anyway, that's kind of a different linear algebra thing that we need to worry later, or should have worried before. So we write rho as this spatial decomposition. So into its projection onto eigenvectors, and then summing over with eigenvalues. Yep. And so J are eigenvectors, and lambda J's are eigenvalues. Okay. And we know it's unitarily diagonalizable, so that those set of J are also normal to each other, and those lambda J. And also because it's PSD. So it's actually PSD, not SDP. Okay, so it should be, we have a little typo here. Positive semi-definite. Okay, positive should be here. Yeah, because it's PSD. Because it's PSD, this also means all the lambda J are greater or equal to 0. Okay. And then we have from the trace condition that so from rho being PSD, all the lambda J are greater or equal to 0, and from the trace condition, we have the trace row equal to 1. And if you trace this thing, it's easy to see that. So just like this calculation, you see that when you trace over this thing, it's just summing over all the lambda j. So sum over all lambda j equal to 1. Okay, and now we see that from those things, so from this equation, this racing here and this racing here, lambda j's can be viewed as probabilities. Okay, so because the probabilities are basically a bunch of values that's greater or equal to 0 and the sum equal to 1. Okay, so if you just rename those lambda j to probabilities, then you can view the lambda j and the j as an ensemble of quantum state, and this ensemble of quantum state will give us the density operator rho. Okay. So here, basically here we give an explicit construction of a PSD matrix that traces to 1 as the ensemble of quantum state. Okay. We say you diagonalize it, then the eigenvalues are the probabilities, and the eigenvectors are the corresponding pure states, and this ensemble will give you the density matrix. Okay. Okay, and yeah. So finally, some final words. So here we find out that we can just so we can totally define density operator without referring to ensemble. We can just say whatever you give you, whatever matrix that is a PSD and trace 1, then we call it a density operator. It corresponds to the classical mixture of quantum states, and then we can do evolution and the measurement on it. Okay, and having this definition allows us to reformulate all the postulates of quantum mechanics. Okay? And yeah, we have like 5 minutes, and I think we can finish. Okay, so basically, yeah, we have our 4 postulates of quantum mechanics, and we can return them all as all in density operator terms. Okay, and so once again, we in our isolated physical system, there is a space, the vector complex vector space called Hilbert space. Okay, and or the state space of the system. And then the state associated with the system can be described by this density operator rho. Okay. So rho is called density operator because it can be viewed as an operator on this linear space H. Okay. So it's a matrix, so you map H to H. Okay. And the density operator, as you just said, it must be a PSD operator. So the matrix must be PSD and it must have trace 1. Okay. Okay. And we also have the mixture of the density matrix written as a postulate here. So yeah. So if your system is in rho I with probability I, then the mixture of this density matrix is summation I pi rho I. Okay. And then, excuse me, yeah, and then we have the postulate 2 that we, excuse me, postulate 2 that we kind of derived before. We say that if your system evolved with some unitary U, then the density matrix evolved into this U rho U dagger. So you sandwich your rho with U and U dagger. So you start with rho, you become U rho U dagger. Okay. And for measurement, we have this more complicated formula. So once again, measurement are described by those measurement operator is a collection of matrix M such that summation M dagger N equal to identity. Okay. And so if you measure a density matrix rho with measurement this NM set, and then the probability, so there will be probability of getting each outcome. Okay, so it should be measurement set. So probability of each measurement outcome is a trace of NM rho and N dagger, or N dagger and rho, because the trace is cyclic. Okay, and so here basically we need to remember the post-measurement state. Okay, so post-measurement state is about N rho and dagger. Once again, it's sandwich your rho with N. Okay. And they need to normalize. So remember, the row needs to have no one, so we divide by its trace. The trace is element row element dagger, and you just use cyclic property to put element dagger here. Okay. So post measurement, measurement probability is the trace element dagger and row, and post measurement outcome is element row and dagger normalized. And if you don't know measurement outcome, then so this is something we couldn't describe before with pure state. Is if you don't know measurement outcome, then the post measurement state rho prime is you sum over all the m and also each individual post measurement state. So and rho and dagger. Okay. And then finally, let's postulate says that you have composite system, and once again, the Hilbert space will tensor product together. Okay, so the physical space is a tensor product of all the component space, and if each system is prepared in some state, then the joint system is in this rho 1 tensor rho 2 tensor rho 1 state. Okay, and yeah. And I guess here we could also have the same postulate for unitary and the measurement that we written before. So you have U on system A, then U is identity tensor U, tensor identity, and this is on the eighth system. And similarly for measurement on system A, then you have those identity, tensor identity, Okay, and tensor identity. Okay, sorry for going over time a little bit, and so that's for the first class. If any no question, let's take a 10-minute break.就是说可以，我会出一题homework跟那有关的。跟那有就这样。对啊，就是可以去算说那个，可以去算你在 teleportation 的时候 density matrix 会变什么东西这样子。所以又是证明题不算吧，是比较像计算题吧，有很多可以算的。很多可以算的。对吧？你可以算各个 density matrix。对。你是连的吧？就有点过敏。对啊。三个 Pauli matrix 可以用这个的线性组合组成一个新的图。那这三个数字一样是实数。因为我看它是对到这个好像三个数字对啊，它只有实数。对。好。然后还有什么？等一下。那三个数字应该是它是一个方向，所以它是三个平方加起来等于1的实数。它在一个球面的坐标。对啊，就球面的坐标这样。这是这个 post measurement state， 它是除以那个积月开头号，在前面一个。
那如果这个几率等于0的话，那这个 postman state 要写成？
它是几率的开根号码，它应该是除以几率，但是
好像是哪里有写几率的开根号，应该是这个。
我想想看，是开根号码，等下我有点忘记。PIS
啊，这是几率啊，所以这是几率。那如果几率是0的话，那这个 postman
几率开根号 ，OK， 好，几率开根号，抱歉，对，几率是0，
还是就没有这个东西，就直接不用写。
比较奇怪的是，可能就不用写吧，因为几率是0，说它很奇怪。
所以就完全。
我想想看，几率是0的话，我也会0除以0。
对啊，就是上面。
我觉得就没有吧。
哦。
上下都是0。
就只有 undefined 是0。
对啊，应该是 undefined。对啊，应该就 undefined。
然后还有个问题就是那个你还会收专题手
？OK 的收啊，对啊。
那个我目前是这样打算，就是我打算考完这个。
你是大几？
我是汉大统计。
汉大统计，你要加入吗？要合作吗？还是
就是我是打算修，然后考完一次段考，然后看我适不适应这个主题。
哦，好，那也可以啊。
如果适应的话，我应该就加进来。
哦，好啊，好啊。
那听说你们礼拜1下午
会有 meeting 在台大632，你可以问小同学。
但是需要看什么论文吗？还是
应该没有吧？我还没有丢给专题生看。如果你们看动画也可以，有一点让你们看。
你还没有？
有吗？还没
看。
还是小同学要直接来加入这个帮忙 review 的行列，试试看。我没有当专题生看过，你可以试试。
所以他也只是去听。
对啊，教同学目前是听而已的。因为主要是课还没上完嘛，还没上完我就当作还在 training 阶段，但是小同学已经看很多了，所以说不定可以来找题目给你做这样子。对。
我下次可以去听一看。
可以啊，欢迎。
不太懂这一题是什么意思？
简单讲就是你量，但假设你把量的结果忘掉，就有点像你就会重新把它盖起来。因为量的话，它会有一个随机的 outcome。那假设它随机了，但是我不知道随机结果，那对我来讲，它就是有一定的几率，这个有一定的几率是那个。像是这里我们好像我们在哪里？下一页没有吗？下面我们就有例子嘛，就例如说这个有一个正的 state， 然后我就要对 computation basis 量，那它有一半的几率变成0，一半的几率变成1嘛。那如果知道的话，那它总之就是变成0或1。但我可以不知道的话，那它就变成一个 ensemble 了。它就是个有一半几率是0，一半几率是1 ensemble， 然后算这个 ensemble 的 mean state 这样子。然后我们说它有一个很简单的 formula， 就是这样的东西。对。但是所以这个是比较 quantum 的事情啊，就是东西你量了但看结果，跟你不量它还是不一样的。量了看结果，量了你就算不知道结果，它还是会变成不同的东西。因为我们就说这个 state 跟这个 state 其实是不一样的。量了之后你不看结果，它已经被改变了。
的确。这个是指什么？
这只是名字而已啊，只是说，如果你是某个正比于 identity matrix 的 state， 我们就要 totally mixed state 这样子，或是 maximally mixed state， 因为后面会就是很简单讲的话，你会觉得就是这 density matrix 的这是一个不太精确的说法，但是 density matrix 你会觉得它的这些 eigenvalue 有点像是它的几率嘛。那样的话，那你如果在 identity matrix 就代表你的几率是平均分布的，那我们会觉得这是一个混的最多的东西嘛。因为如果只有一个东西是1的话，那它就是 pure state， 它几率集中在某一个点上，它是最 pure 的。那几率最分散的就是它是最 mixed 的东西。 为什么变那么大？哎，不对。这样讲一下。Okay, I think it's time to start. Okay, and yeah, so we are going to talk more properties about density operators. So we say that density operator are matrices that with the PSD and the trace one. Okay, and we say well those things this can be used to describe quantum mechanics. And now we're back to a little bit of ensemble interpretation. Okay. Okay, and this is a phenomenon we have seen before. We see that different example of quantum state might give rise to the same density matrix. And if you think it a little bit, it might appear weird to you, but this is what happened. So here we have two examples that looks very different. First example is something Z basis. It's one with probability 0, one with probability 1. And the second example is one with probability plus and one with probability minus. And we see that they will actually correspond to the same density matrix. This is a 1/2 matrix. Okay. And we actually have a theorem to give us a criteria of when does the two example of quantum state give you the same density matrix. Okay. And the criteria is this, okay? And it says that the two different examples, Pi and Psi and Qi and Phi, and they give you the same density matrix if only if they can basically relate it to by a unitary matrix. Okay, so here we have a whole bunch of notation here. Okay. And so we define those tilde notation. Okay, so we want to simplify our notation a bit. So we define the tilde notation to combine probability with vector. This is yeah. So we define the tilde notation to combine our probability with vector. So we say square root of probability times vector means it is a tilde vector. So tilde vector is a vector that's not normalized because its probability is less than 1. Okay, so we combine the probability with vectors, and then we say those psi tildes are related to phi tildes by a unitary matrix. Okay, and yeah, so here we have a bit of typo, so there should be J here. Excuse me. So this is J. Okay, so if psi tilde equal to summation J Uij phi tilde, and where Uij are components of some unitary matrix. So assume you have some big unitary matrix U, and its Ij is rho I column J component is Uij. Okay, and so if psi and psi tilde and phi tilde can be related to this unit matrix, then then if only if then those two ensemble give you the tendency matrix. Okay, and yeah, and here so this theorem seems very simple here, but it has a bit of weirdness in it because you will see this more in the proof because a lot of dimension doesn't match. Okay, so there are basically three numbers that can be arbitrary here. Okay, that is so you have so the dimension. So you have three numbers that can be not matching each other. So you have a dimension of your Hilbert space. Okay, that is how big the Hilbert. So what's the dimension of those vectors? And then you can have a number of I, and you can have a number, I guess a number of psi. That's more precise. You can have a number of psi, okay, and you can have a number of phi I, or maybe let's say phi j here. Okay, yeah. So remember here, although we have been given examples that are very orthogonal to each other, but in reality, those when we are given an example of a quantum state, those psi don't need to be orthogonal to each other. So and they can be heavy. So each psi can have arbitrary relation to each other. So for example, oh, what's going on? Oh, yeah. So those psi can have arbitrary relation to each other. And in particular, you can also have arbitrary number of psi here. We just say it needs to be probability mixture. Okay, so number of psi can be totally independent of the dimension of your Hilbert space and the same as the psi j. And also number of psi here can be different than number of psi j, phi j here. And that can be very annoying to to say even write down this equation here. And yeah, and to make this a little less annoying, so first we make these two numbers the same. Okay, so we try to make these two numbers the same by saying that whichever number is smaller, then we just add a whole bunch of vectors that has length 0. Okay, so the number is same here. Okay, so this makes notation a bit easier. And I should have gone this first. Okay. But okay, so that's one thing we do. But let's go back to an easy example we have. Okay, so the easy example we have is this example of ensemble being 0, 1, and oh, we are missing a parenthesis here. Sorry, control. Yeah. So this ensemble, first ensemble is in 0, 1 basis, and the second ensemble in plus minus basis. And we said we know we have already done our calculation to know that this ensemble gives the tendency matrix as this ensemble. And here we try to write down this equation, right? So we want to try to say there is a unitary matrix to relate those unnormalized vector in first ensemble with the unnormalized state vector with the second ensemble. Okay, so the unnormalized vector of first example is this 1 over square root 2 0 and 1 over square root 2 1. And the unnormalized vector of second example is this 1 over square root 2 plus 1 over square root 2 minus. And we see that so 0 is related to this plus and minus by just adding together times 1 over square root 2. And 1, so you can check this yourself very quick. So 1 is plus state minus the minus state times 1 over square root 2. Yeah. And so here you can see those are the coefficient of u. So this is u00, u10, u01, u11. Here we start our indexing from 0. Okay. So yeah. So those those 4 numbers are our u's. And so when we group them together into matrix, we see our u is 1 over square root 2, 1, 1, 1 minus 1. And they actually happen to the Heidemann matrix. But yeah, it's kind of a coincidence. But anyway, you see that this is a unitary matrix, and this is what we mean by relating the vector set here to the vector set there by unitary matrix. Okay, and now let's start with the proof. Okay, so once again, this is if only if the if and only if the theorem. So there are two directions, and we start with the easier direction where we have two examples. Okay, so we have example those PSI and those QI. Okay, and oh sorry and this direction is okay. So the easy direction is we have this being true. Okay, so either direction we have the example. Okay, but I want to show whether okay. So I want to show that if we have this equation, then let's generate the tendency matrix. Okay. Okay, and so we have that equation, and so we can plug in. Okay, so we can calculate the density matrix on the side part. So this is just the summation i's, PSI, and here we immediately see why we want this tilde notation. Okay, because you can absorb a square root pi to this side and another square root to pi to this side. So we see that this way we can write our decomposition of density matrix in a cleaner form. Is summation of this psi tilde. Okay, and so psi tilde, and then we use our our given equation. We can write psi tilde as phi j, summation of phi j. So psi tilde is a summation uij and phi j tilde. And this psi tilde bra can be similarly written as phi k tilde because we need a different dummy variable. So here we have summation j, and now we give a different summation dummy variable, summation k. So phi k tilde and uik star, because you do complex, you do the adjoint operator. So this uik become uik star, means complex conjugation. Okay. And now we just do change of our summation order and group things differently. Okay. So those are numbers, so you can just write the number next to each other, and then we'll try to do a summation on I first. Okay. So it's a summation I, uij, and the uik star. Okay. And now remember, u's are U is the uij and the uik are elements of unitary matrix. Okay, and okay, and so those uij for some j is just the j's column. Okay, that will be sorry, it's a bit ugly. Okay, so those uij is like the j's column of your u. Okay. And uik is like the k's column of u. Okay, and we know u is a unitary matrix, so the i's column and the j's column and the k's column are orthogonal to each other, and that means that this summation I, so the summation I uij and summation I uij and uik star is actually the inner product between those two columns, but because u is a unitary matrix, the inner product between two columns are 0, except where j equal to k. Okay, and so that means that this thing is delta jk, means that this is 0 unless j equal to k, means that, and so when j equal to k, this is 1. Okay. So each column are also normal to each other, so this summation is this inner product is delta jk. And then the delta function can be so we have a delta function here, and the delta function can be cancelled with the summation j by replacing all the j to k. So this is delta jk cancel with summation j and make a j equal to k. So we just have summation k, phi tilde k, and just like here, we know this is rho phi. And yeah, so this is complete the if iteration. So so if our density matrix, if our ensemble vectors are related by this unitary matrix, then the density matrix are the same. Okay, so this is the easy iteration. Any question? And now let's go to the hard iteration only if. Okay, and the strategy, I should say, so the high-level strategy is actually, I think it's quite simple. Okay, so so what we want to show is that so now our A when we have some density matrix A that's the same as density matrix calculated from psi tilde, and also same as the density matrix related calculated from phi tilde. And once again, because A is PSD, we write A as spatial decomposition. This is lambda k, some k lambda k, kk. Okay, and we also write this spatial decomposition. So this lambda k is eigenvalue of A, and the k are eigenvector of A. Okay, and once again, we can absorb this lambda k equal to k, so we write this k tilde, k tilde. Okay, and so the high-level strategy is we are going to show. So we want to relate psi tilde and psi tilde and phi tilde with a unitary. And the strategy is we use k tilde as the middle. Okay, so we are going to show the psi tilde is related to k by some unitary, k tilde by some unitary, and so let's say u1, and k tilde is related to phi tilde as another unitary u2, and that means psi tilde is going to relate to phi tilde by combination of those two unitary, which is also a unitary. Okay, and well, personally, I think the proof is the core idea of the proof is not too complicated, but the proof is very complicated because we need to deal with the dimension mismatch we talked about before. Okay, and I guess here we have a third dimension here. Okay, fourth dimension here. Okay, so let's say we actually have 4 different dimensions here. So we have the dimension of a Hilbert space and dimension, and I guess this is not quite dimension. Okay, so we have a dimension of a Hilbert space, and we have a number of vector here, number of vector here, and excuse me. And then there is an extra thing that is dimension of the span of the vector. Okay, dimension of span psi I. Okay, and this thing is the same as because we are dealing with the case where density matrices are same, so the span of psi is actually going to a span of phi. But anyway, so this dimension can be different from this dimension, right? Because your psi can be all restricted to some subspace of H over your total Hilbert space, and so this dimension can be smaller than this, and but something we know is some relation is the dimension of the span here is smaller or equal to the number here. Okay, that's basic linear algebra. You cannot span a space that's bigger than the number of vector you have. Okay, and yeah, so it's very annoying. You have 4 or 5 different number here. Okay, and but here the first thing we need to deal with is the dimension of this span is different from the dimension of H. And the dimension of span will basically be the number of non-zero vector of A. Okay? Because your psi I and phi, your psi I and phi phi I doesn't span a full Hilbert space, then the density matrix you write will also not will have full rank. Okay? That means that in terms of this spatial decomposition, you have a whole bunch of eigenvalues that are 0. Okay? And but as you can might imagine, those dimension with eigenvalue 0 doesn't matter, and here we give kind of proof that it doesn't matter. That's because okay, so here we are kind of thinking yeah. We are kind of yeah. So let's give some high-level idea. So our whole Hilbert space is H, and it's going to be split into two parts. So the first one is what sorry, and we're going to prove a different thing. Okay, so yeah, let's write a high level here. Okay, so let's read down as A. Okay, so we can split the space into two orthogonal parts, and so the first part is lambda k greater than 0. So the part you span by k with lambda k greater or equal to 0, and the other part is kind of a null part with lambda k equal to 0. Okay, and what we want to try to show is that, so here what we are going to show is that this part equal to the space we talk about, span of psi. Okay, so we are going to prove this thing equal to this thing. Okay, and or I guess not. We didn't quite prove equal, although I think yeah. Anyway, we don't need to prove it's equal. We are going to show span of psi is inside this part. Okay, and to show span of psi inside this part, we need to show that anything here is not in wait, excuse me. Well, I'm trying to show. We're going to try to show anything here is not inside this part. Okay, so this is a bit convoluted logic. Okay, so I'm going to show any vector here is not inside this space. Okay, and to show that, we say, okay, so we have any vector inside here, inner product with any vector inside here. Okay, so we say for all I, for all psi, so we take any psi here, and we see can it has any component inside lambda k. Okay, if it has any component inside lambda k, then yeah, it has any component inside lambda k, then it should have inner product with its inner product. It should have any component inside lambda k. You should be able to find some psi with this lambda k equal to 0 space. You should be able to find some psi inside here that is a non-zero inner product with UFI here. Okay. And we are going to show this thing equal to 0 by calculating this thing. Okay, so we say phi is some eigenvector with eigenvalue 0. Okay, and then we do is summation on A, and kind of by definition, because A phi equals 0, so this is equal to 0. Okay, and then we go back to use the A decomposition of A as those psi tilde. So we say that. So A as summation I psi tilde. So it's summation I, then it's the inner product between psi and psi tilde and psi tilde psi. And then this is summation I, then psi tilde psi absolute value square. But those things are positive semi-dependent, so those things are greater or equal to 0, and you sum over all of them and they go to 0. That means that they equal to each one of them equal to 0. Okay, so it means that whatever vector psi inside this 0 space, it has 0 overlap with all of your psi. and that means that the span of your psi is has no component in this zero space, and that means that it's in this lambda k space. And so this very convoluted logic. With this very convoluted logic, what we want to say is that this sentence. Okay, so psi can be so yeah. So we use this very convoluted logic to finally say that psi can be written as a linear combination of k tilde prime, where we use a kind of funny notation. So we use it. Oh, wait, does it disappear? So we use this k prime tilde prime notation to mean that it is something inside this space. Okay. Yeah. Okay. And yeah, but I guess we don't really need this prime here. But anyway, we use prime here. Okay. And yeah, so for the yeah, so k tilde basically are defined here, defined for those lambda k greater than 0. Okay, and anyway, we say all the psi on each side is lambda k greater or equal to 0 space, so it can be a linear combination of the eigenbases here, which are the the k with lambda k greater or equal to 0, and I guess that's right here. Okay, so k tilde equal to square root lambda k and k. Okay, so so each side can be written as a linear combination of k, because k is the basis for this space, and also each side can be written as a linear combination of k tilde, because you rescale your basis vector is still a basis. Okay, and yeah, so finally we say psi can be written as a linear combination of k prime, and we can return it as this thing. Okay, so psi tilde equal to summation ik prime cik prime k prime tilde, where cik is just some coefficient of your linear combination. Okay, and yeah, and we use this prime notation to signify that we are only taking lambda k greater than 0. Okay, and yeah. And the next step, so by our strategy here, so next step we want to show is basically we want to show this C sub ik prime is a unitary matrix. It's an element of a unitary matrix. But once again, because of the dimension mismatching, we need to do a bit more work. Okay, and and anyway, here we start with our here we continue with our calculation. So summation I psi tilde I equal to summation k tilde. This is just from they are all same as our density matrix. So A equal to this psi expression, also equal to this k expression. And finally, we use this condition that we had before. So we write psi tilde I as k and c. What we can say about our c? Okay. So psi tilde I. Now we have a lot of dummy notation. So summation I psi tilde I, and so we have our summation I still here, and then we have a dummy variable k prime here. Okay. So we have a dummy variable k prime, and we have another dummy variable. So this dummy variable k prime for this psi tilde I, and another dummy variable L for this for the psi tilde I block. Okay. So this L is like a k prime. Okay. And here we are using a bit of funny notation, but this K prime tilde is like this K prime tilde, and this L tilde is like this K prime tilde. So this is a different indexing of K prime tilde. Okay, and and now the next step. So this equation should show you that these C are orthonormal basis from a unitary matrix, and we use this by sandwiching this expression with some M tilde and S tilde. Okay, so what we do is we sandwich both. We have M tilde and sandwich and S tilde, then sandwiching those two equations. Okay. And so we sandwich both of them inside. So this side we have summation K and tilde this thing, and tilde this thing, and S tilde. And here similarly we have M tilde sandwiching the matrix part and S tilde. Okay. And now remember M tilde S tilde are two different vectors in this state, also normal state K prime tilde. Okay. And oh, sorry. It's actually not orthonormal. It's also only orthogonal. Okay, in the ortho set, orthogonal set, and this set, when you have something like M tilde and K prime tilde, this inner product with each other, we know it's quite a kind of like a delta function. Okay, remember K is also normal set, and so you have K tilde equal to the square root lambda kk. Okay, so you have K tilde squared, then it equal to lambda k. Okay. And so you see that this I tilde j tilde will equal to 0 if I not equal to j, so you have the delta ij. And when I equal to j, then you have basically I tilde squared, I tilde inner product with itself, then you just get lambda I. So this thing is delta ij times lambda I. And so you plug this inside this formula here, and you have a whole bunch of delta here. So here is a delta nk, and you have delta ks, and you have summation k, so this delta nk will just turn k equal to m. So you have actually delta ns, and you have two lambda here that will give you lambda n, lambda s. And similarly on this side you have this summation I, ci is delta nk prime, and you have delta nk prime here, and with this summation over k, just turn k prime equal to m. Okay, so it's k prime to m, and you have lambda m here, and similarly this summation l and the delta ls will turn l equal to s. So you have c of c star of is here, and the lambda m, lambda s here. And yeah, so from those both sides, you cancel the lambda m, lambda s here, and you just arrive with delta ms equal to summation I, ci, and cis. And that means that if you write this matrix C out, then you see that this ci and cis is similar to the relation we had before. This means that whenever you pick the ith column, sorry, the nth column, and the sth column of C, then you see that they are also normal to each other. Okay, so this means this thing is equal to 1 if only if n equal to s. That means all the columns of C are also normal to each other. This is the inner product with the nth column and the sth column. Okay, just like before. Okay, so you see that this matrix C has also normal columns, and but somehow this doesn't totally end our calculation here. Okay, so I want to say that C is so as we said, this delta ns equal to inner product with the mth column and s column, means the columns of the C are also normal. But this doesn't just give you C is a unitary matrix, because the row number and the column number can be different. Okay, the number of columns, so number of columns here are indexed by I. Okay, and this go back to this thing we talked about here. Okay, So the length of the column is the number of sides here, and the length of the row is the dimension of side is the k. Okay, it's non-zero. Is it's a non-zero number of non-zero eigenvalues of A, and which basically means basically is the dimensional span of psi. Okay, and so we know this thing can be smaller or equal to this thing. Okay, so C might actually not be a square matrix, but that is okay because we can just extend C to a unitary matrix by appending zero columns to the right. Okay, and by appending also normal column to the right. And so that will just transform C to so that way you can define a unitary matrix C, and that will transform your and those extra columns basically will transform into this lambda k equal to 0 subspace, and so that doesn't change your A equal to summation k lambda summation k lambda k equation. Okay, and so finally we got our unitary matrix C, and so we have psi tilde equal to summation k ci k tilde. Okay, and then we can wrap up with this very long derivation with the intuition we had before. So we have psi tilde equal to summation k ci k tilde, and we just say well, psi tilde and phi tilde basically has the same relationship to k tilde. So we can find another matrix W such that phi j tilde is summation equal to summation k wjk k tilde. Okay, and so we append, as we say, we append zero vectors to the list of k tilde. Okay, that corresponds to all those eigenvectors with eigenvalue 0. Okay, and this gives us that as we said before, so this psi tilde. So psi tilde can be written as summation k u I j and phi tilde, where our u is just basically the combination of the C unitary and W vector unitary. So you have a W dagger to transform your phi tilde to k, and you have this C to transform from your k to psi. Okay. And here is a bit of equation to do this calculation. Any questions for this very technical derivation? Yeah. Okay. If no question, then let's go to a bit of more interesting part of this lecture. Although we have a short time, so I think we will continue next time. But let's start with the idea. Okay. So we have an idea of a reduced density matrix. Okay, and this is also something we kind of seen before. Something we kind of seen before. That is, if you have an entangled system, then you can describe part of the system as the density matrix. Okay. So you can describe a system or a composite system is usually entangled state. Okay. So suppose we have two systems A and B, so just like before. So like you have Alice and Bob. Yeah. You have Alice and Bob, and they share some entangled state, so maybe they share an EP up here. And then you can, so this state is some state that can be described by the both of the system, right? Because we say it's an entangled state. So it's 1 squared root to 0, 0 plus 1, 1. Okay? So the idea is that this is an entangled state. And we say entangled state doesn't equal to some pure state psi tensor some pure state phi. Okay? And so you cannot describe the part of the system behave as a pure state. But actually, we find out that we can describe what B can do on itself by a density matrix. So if A and B share an entangled state, and they want to see, and A doesn't send this state to B. So if A just holding this and never give it to B, and there are still something B can do on itself, then that will be described by a density matrix, and which we call the reduced density matrix. Okay. Yeah. And here we have a very general formula. So let's assume we share not only a pure state. So let's assume we have A and B share the entangled, possibly entangled density matrix. So if some density matrix rho A B share between A and B, and we want to know what is the state B hold can be described. Okay. And we see that is described by this operator. Actually not on B part. Here we read on the A part. So what is the season A hold? How the season A hold can be described, and it's described by this reduced density matrix rho A that can be calculated by the trace B operator. So it's trace B rho A B. Okay, and trace B is a map. It's called as a partial trace on system B, and we see the partial trace is defined here. Is basically you do trace on the B part. Okay, so we see that if our system is not entangled, so if we have a not entangled mixed state, so it's it's on state A1 A2 tensors on state B1 B2, and then we define a partial trace on such state as you trace on the second system. Okay. So it's A1, A2 still on the first system, and you trace the second system, and this becomes a number. So it's just B2 inner product is B1 times A1, A2. Okay, and this definition only defined on very special kind of state. So we only define a state as kind of a tensor product with each other, and we extend this definition to all density matrix by saying, oh sorry, here I have a typo because it was density matrix. So I should say, sorry, this is not quite correct because the first one was density matrix. So I should say trace B for any rho AB plus any sigma AB equal to trace B of rho AB plus trace B of sigma AB, and this is the same for every density matrix. So you get any density matrix, and you can read it as a linear combination of this form, and write down and calculate trace B, and then you linear combination and back. Okay, so yeah, so that's a reduced density matrix, and and here we talk a bit about its domain and range. So you have a composite system is it has a Hilbert space that's HA tensor HB, and then basically what we want to say here is density matrix, or sorry, the partial trace operator. So if you partial trace all the system B, we will map some density matrix on AB to density matrix on A only. Okay, and I think here I should also say rho A. Okay, up here. Okay, and yeah, so you will map some density matrix on both A and B to, and here is also a bit wrong. Okay, so it should be a linear operator HA tensor HB to a linear operator on only HA. Okay. And let's see an example. And example, so suppose we are in a pure state, okay? So we want to see as we said, so the example kind of see. So the reduced density matrix of this EPR pair beta 0, 0. So we trace B of this beta 0, 0. And remember beta 0, 0 equal to, so the pure state one is 1 over square root 2. 0, 0 plus 1, 1. Okay, and so you write it into density matrix. It has a lot of terms, so you have 1 over square root 2 from the broad part and 1 over square root from the cat part, so you have total 1 over 2. And so you have those 2 cat and those 2 broad, so you have 4 closed terms. So 0, 0, 0, 0, and 0, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 1. And then you do trace B on all 4 of them, because each one of them is in tensor form. So you do trace B on all 4 of them. So here the trace B, so B trace become inner product between 0, 0, and you will left with A part is 0, 0. And here the trace B is inner product between 1 and 0, and you left with A part is 0, 1. Here you trace the B part is 0, 1, and A part left with 1, 0, and finally you have inner product between 1, 1, and left with A part on 1, 1. And then you see that this inner product is 0, and this inner product is 0, okay, because this is 0, this is 0. And the other 2 inner product is 1, so you left with 1 over 2, and this projected 0 state, and this projected 1 state. So this is 1 over 2 identity, which is a totally mixed state. Okay, and we actually have time to finish this. But any question on this example? So this is a density matrix on B. That means that whatever. So for example, if B do measurement, so sorry, I keep mixing up A and B. So this is a reducing density matrix on A, and I should write row A here instead of row A B. Okay, so it's row A here. So row A, this is reducing density matrix on A, and that means if Alice do some measurement on her part, and she should calculate according to this thing. So in particular, so for example, if Alice measure X operator, then you will give you that 1/2 probability. 1/2 probability giving the +1 outcome, and 1/2 probability give you -1 outcome. Okay. Okay. Yeah. And so 1/2 probability will give you a +1 outcome, and the resulting density matrix will become plus, as we say, and the resulting density matrix on Alice's part will be minus. Okay, and okay, and here we give a kind of schedule, I guess a kind of a theorem that says that the reducing density matrix actually describe all the measurement outcome on a subsystem, but this is why we like the reduced density matrix, because it describes a subsystem over your entangled system. Okay, so so this means that if you so this means that you have A and B share some entangled state, and we just want to see what if Alice just do things on her part itself, then we can just calculate the reduced density matrix to see what the measurement outcome Alice can get on her part. Okay, okay, and here we have a kind of funny proof here. Okay, and this proof actually uses some physical intuition. It's a bit convoluted logic here, but I kind of like it because it has some physical intuition inside. Okay, so the kind of proof here is we say that what happens if you measure B in computational basis. Okay, so we have A, B shares on system, and we measure B in computational basis. Then we'll find out that the system A will collapse into the reduced density matrix. Okay, And so the mass is here. So we do measurement of computational basis measurement on B. So measurement operator are identity A, tensor those computational basis projectors. And okay, so let's keep the mass a little bit, and you see that the end result is that the density matrix on A is the same as this identity. We have some typo here. Is summation I and identity tensor is identity and this II sandwiching your row AB. Yeah, this II sandwiching your row AB, and this equal to this equal to your trace B row AB. Okay. And the physical intuition is that A and B can be really far from, okay, so A and B can be really far away from each other, and so B doing measurement on her part or his part shouldn't affect A doing measurement, okay, so because they can be really far away from each other, and by the principle of relativity, if they are really far away from each other, whatever B do should not affect the information on A. Okay, and so B do computational basis measurement. This will collapse A equal to the density matrix, reduce density matrix rho A, and that doesn't change the A's measurement outcome. That means even if B doesn't do this measurement, the measurement A do is the same as the measurement on the reduced density matrix of rho A. Okay, and yeah, sorry for going over time a little bit. And any question? Otherwise, we'll continue with purification on next week, next Tuesday. Okay, so see you next Tuesday.抱歉，这样。好，等一下，我先关一下。